have Siddharth Mathur. He's the CEO and founder of Fast Track. And he's going to show you a very, very interesting product that they have. If you think of Google traffic, except he's doing it for mobile. Oh, sorry.
I'll give you the mic.
Okay, testing. Okay, sorry. Yeah, he's taking, if you think of Google traffic, he's doing that for mobile networks. He's very excited to show you his product demo. He's an implementer and active at W3C and 3GPP, and we want to try and get him into doing IETF work as well. So thanks so much, Siddharth.
Okay.
Yeah.
Yeah, this is fine. Should I use both, Dhruv, or only one?
Just one.
Okay, keep the other one.
Yeah.
Okay, so good afternoon. I hope this is a welcome change from what we've seen thus far during the day. This is more consumer-centric and how you as end users use 4G networks every day on your smartphone. And I hope that all of you are smartphone users because you are networking nerds for sure. So I hope that you have strong opinions. Oh no. Okay, I probably wrote software for that as part of my Nokia job 10 years ago. Okay, so a non-believer here for sure, but that's okay, we'll go forward. So what we want to talk about here is how standards and protocols and stuff we do work in real life. And I have had a fun journey over the past 15 years, starting from the lowest layer of the stack. I studied signal processing and communication systems at University of Arizona, and I learned multiple input, multiple output in MIMO systems, and all the core protocols and signaling systems that make up modern 4G and the next generation of networks, and that are still in the process of being deployed at large scale. So I started off at the signal processing and comms layer, and then my first job was building video streaming systems in the US at a startup in Boston. So my first job was about doing one of the first few apps which did video streaming using 3GPP. That was RS5 at that time, release 5. And they had RTSP and other transport layer streaming protocols specified as part of their packet level series on how to build and roll out video streaming over UDP. So my job was to be the codec guy, the compression guy. And of course, I wrote codecs in C and C++, but half my job, because it was a 30-person startup, was also to deploy streaming servers on the internet and make sure that people on handsets in the US, and most of the networks were still EVDO and 1x RTT, for those who remember the early days of CDMA and GSM. And those were basically pilot video streaming commercial deployments at an application level for US consumers. So I started with that, and then I drifted on to doing basically WebKit work. And WebKit, as some of you might know, is what makes up your Chrome and Safari browsers, right? So it's the web presentation layer. And the beauty with this presentation layer is that it's actually remarkably sophisticated and practically a full operating system within it. And it's by itself, WebKit is just a renderer. It parses HTML documents and spits out an image that your graphics card can render on the screen. But that by itself is not terribly precious, right? What you need to do is put a UI around it, call it a browser, put a stop button, a reload button, an address bar, or if you're making it for a Nokia smartphone, where I was working when I worked on this, make sure it's slick and smooth and can compete with an iPhone. Because Mr. Jobs was unhelpfully, brewing a revolution in touch interfaces at that time when I was at Nokia R&D in Boston. So the engine itself, or the core tech itself, is not terribly interesting, is what I learned the hard way there, even though I was working on probably the world's most complex software by the sheer number of lines of code, by the complexity of the compiler required to just compile the damn thing, and the weight on a phone when you embed this large piece of software on a small smartphone at an affordable price point. So my journey has been about implementing standards, starting with the 3GPP series and figuring out that real world deployments are really hard. that this Kuwait Telecom has the Cisco gear, but they have never applied the firmware which actually enables the UDP ports to be opened dynamically based on whatever is written in the spec. So there is always a very large difference between the spec and what's implemented in firmware at a given network. And that was sort of my baptism by fire in the early part of my life. And as I moved into the web area, I realized that W3C, which is the World Web Consortium, is much faster and nimbler in moving forward with standards. And after the HTML4 and the IE fiascos, they said HTML5 will be a working, living standard, and we'll be constantly updating it every few months or every few weeks. And people are welcome to implement it, ship it, and we'll make it agile, so to speak. So a lot of my work at Nokia was about implementing W3C standards, which in modern day we call HTML5, right? So HTML5 working on a phone, not on your laptop, was what I was doing. And optimizing for performance. So making sure the HTTP protocol worked fast. You could download documents on the web over a high latency connection, caching things intelligently at the HTTP level, and basically managing memory for JavaScript engines and basically low-level memory management stuff for the Symbian OS operating system, which was the default at Nokia at that time. So moving on, I came back to India about 5 years ago, and I started working for emerging market-oriented services. And this was, again, at the application level. And then a few years ago, I founded Fasta, which is where I'm the founder now. And part of the rationale was that there is huge amount of scope to simplify networking for application developers. And I had, at Nokia, being a consumer-centric company, I built a lot of sympathy for how end users use the internet, because that was the time when India, Indonesia, all of Southeast Asia, Brazil, they were eagerly buying smartphones. They were eagerly adopting 3G networks for the first time. And there was an incredible explosion of first users coming online. And that what has happened is that with the geo revolution in India, that has only accelerated for us in this country. And I don't think that is showing any signs of petering out anytime soon. And if you look at the IPv6 stats on IPv6 adoption, I was looking at the AppNIC statistics. AppNIC, as you know, is the registry which hands out IP allocations to companies. So if you look at AppNIC's statistics on IPv6, India was nowhere a couple of years ago, and now it's like 50% of the world's IPv6 users are in India, and that's the gentleman here is probably representing that boom. So it's just mind-boggling the rate at which this country is moving. But at the same time, one could argue that the quality of service and hence the quality of consumer experience is still very poor. It's very fragmented in availability when I talk about availability as in geographic spread. But even more importantly, if you normally have a 4G LTE network in, say, outside this hotel at Marathalli, the quality of service is extremely poor. And that is what we are trying to do. We are trying to figure out basically what can we make which looks like Google traffic. And what does Google traffic do? It shows you where the traffic is slow in a red line, where traffic is fast with the green line, and where traffic is okayish in an orange line. And our ideal vision is to get as close as that abstraction as possible for normal consumers, and by extension to API users who are our primary TG or our target consumers for our product. So as a startup, we want to build APIs for developers and make it easy for them to focus on what they know best, which is sending data down the pipe. And as Dhruv said, they have a tendency to believe, correctly I would say, that this is a dumb pipe. But then dumb pipe doesn't mean that there are no nuances in it. It's just that it's too hard for you to understand and abstract for proactively. So how do we give them better tools and APIs to abstract it intelligently while we hide that complexity for them is what our broader goal is. And the work that I'll show and some of the visualization is one of the baby steps to get to that level of synthesis. So overall, I'll talk about some broad trends in mobile internet traffic. Some of them I've already mentioned, but this is from a Cisco slide, and we have some Cisco friends here. So welcome, hi to you again. So this is from Cisco's slide at Mobile World Congress last year, and I just want to put this here to show the big people's, the big daddy's perspective on mobile internet usage and growth. And what this says is on the left side that the world has gone mobile and Wi-Fi, and 63% of IP traffic will be originating on mobile and Wi-Fi, right? So that's a spectacularly large amount of traffic. And on the lower half, for those who are unable to read what's on the left, it says internet traffic growth is at the edge. And at the top, it says metro growth traffic is up 35%. And 15% regional traffic growth to 23%. And cross-country traffic is on the decline. And why is that is also something which is pertinent to what I'm going to talk about. Because what computing is doing in the smartphone era is that your IoT bike has a computational node or a connectivity node on the lock, right? So we have the pedal CTO here, and their bikes or their connected platforms all have a SIM card or a data card or a connectivity, and they talk to the internet. But that is within the city of Bangalore, and all the people who are using that are also in the city of Bangalore. So that counts as basically metro traffic, right? So metropolitan Bangalore sources and metropolitan Bangalore endpoints. Or conversely, if you're in San Francisco and trying out one of those the scooters by Uber, you are renting that scooter, the scooter is talking to the internet, and you are talking to the servers that Uber runs locally within San Francisco, and it all stays within that. So there's no traffic going to London and coming back, or if the scooters were in London, there's no reason for that traffic to originate substantially out from that area. So social impact of technology has caused this movement, and that's what we're going to shed more light on in the context of mobile networks specifically. So we've already mentioned that this is how Bangalore's 4G networks appear to appear to work like for us. They look like gigantic speed bumps. You never know when you have a dropped call, even more so when you're doing a WhatsApp call or a packet data call. You don't know when your browser will stop loading a web page. You don't know if you have a VPN in a cab. We're talking about sitting in the back of a cab and trying to get work done on a VPN, when your VPN will drop, or it will have to retry interminability to get anything done. So we experience all of that every day. And now taking a broader view of how or which regions of this country or the world we're trying to build for, we're trying to map Southeast Asia and South Asia to start with. And we have about 80 cities covered in this part of the world. And it has obviously 1/3 of the world's population, so it's extremely important from a justice and fairness perspective that this is all working beautifully well, and these are deployed and operated in a manner which is high quality. And even from a consumer rights perspective, do the regulators in each country have the right tools to make sure that what's being sold to the consumer is actually what's being delivered to the consumer? And since I lived in the US, I understand that there is a lot of transparency in how US carriers sell their services. They always have had coverage maps on their website prominently displayed. But also that the regulators have been technically savvy and willing enough to enforce quality of service and coverage with those services. So, but in other countries, specifically in Asia, there has been regulatory oversight for data services has been very slow on the uptake. And it's not clear that beyond isolated testing of data networks and latencies and kbps and mbps, the regulators are well equipped to make decisions at a massive scale. So livelihoods have started depending on 4G networks, and that's why this region matters to us the most. As you know, that Uber and Ola have become huge employment generators. And from a mobile marketplace perspective, if you think of Uber and Ola being basically a two-party system where your driver is on a smartphone, and that smartphone needs to be up on the network, and only then will that server, let's call it a server for the sake of discussion, that server needs to have uptime. Only then will that server be reachable and pageable. So if around this hotel, if there are 5 drivers and only 2 of them are pageable by a low latency connection from Uber server, only 2 of them will be candidates for for your next request to that platform to be matched with you, which means that about 3 out of 5 of their capacity is not available for ride allocation, which is a huge economic cost for efficiency of a real-time marketplace. So the more real-time marketplaces we have, the more the economic necessity of having smartphone uptime goes up, and having predictable quality of service goes up. And perhaps at the consumer level, if you happen to be a driver partner on these platforms, do you have the tools to make a quick decision? Am I getting a low latency connection right now? And if not, what can I do to move around or do something so that I'm perhaps in one of those green zones which imply low latency and not one of those red zones which imply either high latency or high congestion. So it's from an economic and social perspective, it's never been more important. And as our transportation infrastructure grows, like we discussed, these bike sharing and scooter sharing are up, and they're going to be deployed in even more massive scale in India and Southeast Asia. Singapore is already doing a pretty good job. China has already gone big on this. These are key components of how urban mobility will work. And when you think of congested cities like Bangalore, these are going to be extremely valuable things to have a small bicycle or a scooter or a moped, which is connected and can efficiently be checked out from place A and dropped off at place B. And it knows where you traveled. So when you have a meter at the end of the ride showing that you're going to pay 100 rupees, that meter actually shows you the right fare at the right time. So this is a critical infrastructure for all of us. Again, we are putting a quality of experience filter on it because we're talking consumer stuff and also application level perceptions of quality and user experience. So think of all that I say with that top-down filter, not a bottom-up filter. So latency, we know, is the milliseconds of ping time, for example, for a packet. And we can think of ping time here as the milliseconds it takes to go from your smartphone to the nearest data center. And for the sake of discussion, we use data center as, say, Amazon Web Services in Mumbai, or Azure in Mumbai, or Google Cloud Platform, or a CDN node for, say, Akamai in, say, Chennai. Right? So we think of these as what an application developer would be easily able to deploy to if he or she were writing code. And we know that by analogy, this is what latency feels like. And if most of the packets or most of the cars in this case are delayed by most of the time, that's basically a very high median value of round trip time. And this is a pretty solid analogy for routing delays. And the other thing that we also understand from quality of service is how many packets get lost in transit. And as we know that that's usually a factor of packets not being able to make it across a router usually. And that might be your Wi-Fi router if you have too many people watching YouTube on the same Wi-Fi access point. Or if you are an ISP or a telco, your routing nodes are congested and they're dropping packets. So these constitute basically failure points within the user experience chain. So from a consumer's perspective, you want your apps to be fast. And as we probably know by now, congestion and latency have a direct bearing on TCP performance. And TCP performance is what HTTP performance depends on. And then we'll get to the point later on how people have been building Quick and other alternatives to full HTTP and what happens with those. But from a consumer-centric perspective, you want your apps to be fast and your Uber or your Ola app to find the nearest cab really fast and not have those moments when it says try again because I couldn't find a cab even after 5 minutes of searching. And that happens. I was discussing with somebody this morning and they echoed exactly what I told them. I was thinking myself that for the past 2 weeks, Ola has been taking forever to find me a cab. And I find it hard to believe that there are no drivers on the roads who are serving that request right now. And Uber always manages to do a match. So it has to be something about that their supply side is not online enough, or they have a bug in their real-time matching system, which I hope they can fix. But if it is infrastructure and shared infrastructure, it better not be that their driver partners are not reachable at all from their servers, which is the worst way to run a highly real-time marketplace. So from how we do it at Fasta, how we build a mapping system which deals with QoS and QoE, we again prioritize application perceptions of it, and we again measure ping times to the nearest cloud, the public cloud, not just say Airtel server or Jio server or any operator server. We try hard to be operator agnostic. and make sure that we are talking in terms of what an application user would want to see, or a developer would want to see. Because developers don't want to think about specific operator networks or carrier networks. We currently are measuring these variables from about 200,000 smartphones, mostly in Southeast Asia, which means Indonesia, Malaysia, India. India South Asia, but Malaysia and Indonesia, and some in Singapore and Thailand. So that's our coverage right now. And we are trying to build developer-friendly SDKs and APIs to abstract that information in a manner that's easily consumable by, say, a Book My Show developer or any consumer product you can think of, or Savan and Ghana who want to stream music streams to you, or say Google Ads or InMobi who want to send a video ad to you, or Twitter when they want to show you a video file, but they don't know which bitrate to start off the session on. And video protocols have had a long time to develop semantics to catch up the available bitrate, the bandwidth and the bitrate to each other. But when you start off a streaming session, you don't know what the user's network is going to be like. So you usually start off with very crude heuristics. And those crude heuristics means that your video is buffering for 10 or 15 or 30 seconds, rather than buffering for 1 second and starting the first frames render immediately. So a lot of the steady state video solutions that IETF has built over the past 20 years don't work very well for new forms of consumption, which are typical on smartphones. And from a data pipeline perspective, we write a lot of software in Go. Go is a programming language which is sort of like C. It's more fun to write. And Elasticsearch is what we do a lot of slicing and dicing on. So I'll do a demo on how Singapore looks like on our quality of service maps. And I'll switch tabs to the browser to show you how big is the look. Can I hide this right bar? If I right click on it, does it make it bigger? Lock the taskbar. There you go. Go. Don't hover over it. This was fine? Okay. So what this looks like is, this is a Singapore map, right? And okay, so the demo was copied to this server, and it's, I'm sure, not going to work right now. Okay, I'll change something real quick. I apologize for the snag. Oops, are we offline? So I'll talk about how this data works and looks like, because I don't need a screen to talk about that. So this topic is generally of interest to regulatory bodies too, because they all want to assess objectively which networks and which commercially licensed operators are doing their job in terms of delivering quality of service, or for 4G or 3G customers. So there are many variables and biases in crowdsourced data, and we are basically doing crowdsourcing because our SDK runs in these 200,000 devices that I mentioned, and all of them are highly heterogeneous Android phones at the moment. There are no iOS phones in the mix, and there are numerous subtleties on how the performance of a dual SIM phone, for example, and as we all know, probably half of you in this room have dual SIM phones in your pocket right now. It's up. And dual SIM phones have these really particular characteristics where if your SIM is inserted in the secondary SIM, the radio access it gets from the body of the phone, or the antennas which are wrapped along the periphery of the device, it's not as superior as what the SIM gets when you're plugged into the primary SIM of the phone. So that has historically been done by device makers to save on material costs for radio engineering, both putting antennas in the frame of the body as well as to save costs and volume both, and perhaps power. So there are also issues about when a call comes in onto a dual SIM device, does the device drop the data connection completely in order to accept the call? So there are many subtleties in how practical radio networks are deployed and how real-life consumer devices measure latency and quality of service. So it has its defects in how crowdsourcing being an accurate indicator of not of measuring and quantifying QoS and QoE. But our experience has been that as the law of large numbers catches up, we are able to accurately identify dead zones within Bangalore very easily. And when we do drive-by testing and other forms of just being in the back of a cab and trying to use the browser, and we see our maps and see whether, for example, St. John's Hospital near Koramangala has a dead zone outside, it's pretty spot on that there's a large chunk of red in that area, and that happens to be a very strong dead zone. So the more samples you collect, the more the observations and the means that you're calculating catch up with reality. So this is an area where the unreasonableness of large number of data samples is actually very helpful in aligning what is actually happening on the ground with potentially inaccurate individual samples. So we can never guarantee that a dual SIM device will be as reliable for a ping host as a single SIM device or perhaps an iOS phone. But again, the emphasis is once you have, say, a month of data or 2 months of data or 1,000 samples from a particular part of the grid on the map, do those numbers catch up with the reality in that grid? And our observation has been that that is already happening, and that's a pretty accurate way to do it. And this has largely been done for coverage, which means signal strength. In most countries, OpenSignal and some other companies in the UK do a pretty good job, at least for those nations, in terms of mapping ping times and latencies. But we find that their maps in India are really inaccurate, and our fidelity with catching the dead zones and the live zones and the good zones is actually superior to that. So for example, this is so this is Singapore's map, right? So what does this show you? These are about 70-meter big cells, and these cells are not necessarily your cellular cell with a circle around them. These are just a uniform segmentation of the map of the whole city of Singapore into hexagons. And why hexagons? Hexagons are good for mapping because hexagons have these symmetric property around the center. So any point you quantize within it is not going to have more than a similar amount of error based on probability on where it was actually. So it has, and unlike a circle, if you stack circles next to each other, you'll have dead zones in the middle which don't belong to a circle. So mapping and GIS folks would know this, but hexagons are their favorite shapes because they lend themselves to binning samples geographically very conveniently. So I'll let's see if this reload works. Pray for me, Dhruv. Yes, yes. So this is for M1, which is one of the leading operators there. And actually my demo was supposed to show an animation, but it's, I think I copied to this device at the last moment, so it's showing some. But I'll show you a non-animation actually, because that's equally interesting. So this is the city we are in. There you go. And as you can see, this has a bunch of red, right? And I mean, this is real red. I mean, I can assure you that I live in this part of town, right? This is Iblur, Belandur. And I can assure you that this cluster of reds that you see in this vertical line are actually the access road which I take to my house every day. And no Uber driver has ever been able to finish my ride or start my ride in that lane. So it's not just me, right? And these are about hundreds of thousands of samples from tens of thousands of phones. So it has its limits, but it also has truths that it speaks all the time. There is this, again, this corridor that I take near the St. John's Hospital heading towards Forum Mall when you're coming from the east side of town. And the strip of red dead zones is basically exactly in the same state every day. And this has been the case for a year. And you have to wonder why has nobody figured out how to fix it. And this can come in many forms because you have to appreciate that while at the radio level, this may be about congestion of the spectrum, right? Because your device has to ask for permission from the base station that it has data to transmit. So there is a lot of song and dance to acquire a slot of spectrum to transmit data. But at the same time, there are things that you need to do as an operator to make sure that your handoff of your user terminal is occurring from node A to node B, right? And if you have an IP connectivity, either that data context has been transferred, or if there's an IP address which needs to be transferred together that was assigned to the client and is visible to the rest of the internet, that IP also needs to migrate. So it sort of boggles my mind that that neither are we able to plan for congestion in repeatable patterns, but also we are unable to route our traffic effectively to the backhaul. So this is, I don't claim to have answers for this, but what we are building here is basically a crowdsourced map of quality of service. And this uses both latency as well as congestion. And congestion, like I mentioned, is packets getting lost when you're sending them from the smartphone. And that usually happens either because you couldn't acquire a slot from the radio layer, or some of the intermediary routers, either in the base station or in the backhaul, basically drop that traffic on the way back to the routing points. You want to ask a question?
Yeah, I have a great. That's a great and interesting map. I'm curious about a couple of things. First of all, is actually, you get. That's exactly what I was going to ask you to do. So you see a marked difference between carriers.
Yes.
Right? And then the other question I was going to say is, and this is sort of market by market, do the carriers tend to share towers in this region? Because if they do, that says one thing, and if they don't, that says something quite different.
Yeah.
And also, are you keeping track of battery usage on the device? Because that gives you some notion as to how the device is straining to communicate. You've got a lot of retransmits, right? All of a sudden your battery consumption goes.
No, so about my question about the last point is the battery, is that, are you saying that the trans error rates for the modem will go up, or is the modem programmed to transmit at the constant power level whenever it's in the up state? I would presume it stays at the same energy level independent of the battery's state. That's why the operating systems try hard to shut down the modem whenever the battery is low.
Well, no, actually, you're attenuating your signal based on the location of the cell. So one of the things you can test against is, do I have a data path problem in terms of between the cell and your home office, right? Or is it a data path problem between my cell and the tower? And if you're seeing battery consumption drop, then you know it's between the cell and the tower. Actually, it's not entirely true, right? If you're dropping packets, you're going to see that battery consumption go down anyway. But
that is that a cause or is that an effect?
It's an effect. The battery consumption is an effect
of retransmits.
Of retransmits. So it's just instant. You can keep track of that as well.
But that doesn't answer the root cause of the packet loss, right?
No, it certainly does not. But it gives you a couple more data points as to maybe.
If the tower gives you an act, then you don't retransmit at that level. You don't use that.
Right. If the tower is acting, right. But if you're doing end to end and you're failing there, you have to retransmit anyway.
But then you don't retransmit and use batteries if the tower gives you an act.
It depends.
You packet later on.
Then you still have to.
But you retransmit at an application layer rather than at a layer 2.
That is absolutely true, but you still have the battery impact.
Right. You do have the battery impact, and this is a diagram I took from Ericsson Research's blog. So this is your packet, this is your UE, your smartphone. And when I write data into the socket, the modem is told that there is you need to ask for a slot, and then the phone says to the ENB, which is the base station, that please give me a slot, and then you get a grant of a slot, and then once you have a grant of a slot, you're allowed to actually shuffle those bytes of the packets out to the wire, to the radio layer. And now you have slung them hard enough that the base station can catch them, right? Exerting enough power, presumably appropriate to get them over the network.
Right.
And radio networks also have error correction and other stuff, which is transparent to the kernel generally, to the networking layer of the Android or the iOS operating system. And then once you're there, then of course you have these packet gateways and other backend parts of the base station, and then you get to the packet gateway, which is the second thing on the right. PGW, that's the packet gateway. So if Geo's tower is what we're talking about, they would have a router for a given part of Bangalore, for example, which collects traffic from a few nodes and then shuffles it to their own backhaul and then to the rest of the routing network. And this is the app server. And we are here, right? So we are running off a Mumbai Amazon Web Services node.
When you see those threads, do you really see a signal strength drop to the lowest, or is it signal strength is showing but still the data is getting?
Excellent question. So my Bangalore story specifically is that our signals are routinely 5 on 5 bars, but our packet loss rates are over the hill, over the top crap. Right? So it's either radio congestion or that the backhaul is not shuffling them adequately to a routable point. And it doesn't seem to change dramatically.
So the battery usage will give you a hint there too.
Sorry, which
Battery usage.
battery will give? Okay, I'll take a look.
So a question on that diagram.
Yeah.
Do you, because you're running this over TCP?
These are UDP datagrams.
This is UDP. So at your app server, do you don't do an acknowledgement?
Yeah, so it's a regular ping, what you would do
so
from
you're
the
going to
ping
acknowledge.
command.
So I'm curious to know, are you recording how often you get the data from a given probe, but then the probe has not reported that it received an acknowledgement? So that you know that you have a one-way path all the way there, but that somehow it's lost on the way back.
We're not that sophisticated yet.
Okay.
So if you're saying, can you triage an uplink loss from a downlink loss?
Yes.
Effectively, right? No, we're not doing that yet.
Because also the tower gets to schedule its own packets and tends to know more about things. And the other question I had was, are you getting much response or help from the public cloud providers to actually provide some, places that you can actually more reasonably make statements about? So for instance, they might provide you, say, okay, here's a server, but it's only coming in through this particular uplink of the data center, so that you can know it's coming this way versus it came this way. Are they helping you at all that way?
No, we're not that sophisticated yet.
Oh, too
So
bad.
we consider it to be a black box, where sufficiently paid network engineers are inspecting every packet coming into their router with a Hawkeye, and assuming it's a constant function. And if you sample it long enough, that noise is your constant bias and not a variable bias.
Right. Of
It's
course.
not a
Makes
noise.
sense.
It's not a measurement noise. It's a fixed bias. Over sufficiently large numbers.
That might also provide clues to the network operators and to the Ubers and the whatever as to which peering is more valuable to them.
Yes.
Right?
So we're not that smart yet. We hope to be one day, but not yet. So anyways, I'll keep it quick. I think it's so I'll wrap up.
Can I ask just one
please.
Just a related question. I think you already asked. Now you are reporting if there's a red or green based on what is the data loss which you see start from the UE, which is you have 3 segments of the network. One is the radio network, and then the backhaul network, and then you have a cloud where a cloud may be in the operating network, maybe outside, maybe internet, right? 3 segments. Now you look at the measurement of the packet loss or latency and finding, okay, they are exceptionally high, and that is how we plotting green to red, right? That's the understanding. Now, do you have the mechanism where you can see whether data loss is in the radio network or the backhaul network or in the cloud?
Yeah.
And then possibly, if suppose there is a problem in the cloud, okay, and then you are showing here in the report it is a problem with this network, with this operator, okay, possibly it is skewed information. do not give a real representation with the limited information which you have from the slide.
Right. So we don't is the short answer. The answer to that, we can't isolate it, that we discussed already. And from purely our work's perspective, we can't do that easily anyways without the network operator saying, okay, St. John's Hospital is always a dead zone 365 days a year. What am I doing wrong here? Or every WhatsApp call that starts from this part of that zone, traversing through, always drops its IP address. And why is that? And do I have to debug my radio engineering and network engineering? So the short answer is no. But from our product's perspective, what we aspire to build is primarily intelligence at the application layer. So we want to make it faster. So if a request is coming from, say, Juhu Beach in Mumbai, we know the IP belongs to this operator. We know their expected latency is this. And this is the bit rate your video session should start at. So it has a 1 second time to first frame. Right? So we want to make sure that you can predict the network's QoS for the last mile. We don't care for middle mile and the first mile. Akamai can help yourself to that, or CloudFront can do that, or whoever the big daddies or CDNs can do that. We want to add a layer of last mile awareness that applications can use with one API call. That's our mission. And how to fix it and how to debug it is not something at this stage we are concerned with. And I would think that the operator should think about that more clearly.
Yeah, I think it's a good initiative. By the way, I'm Ramesh from Lanji. I would like to talk further with you.
Nice.
Maybe after that.
So the good news is your latencies in Bangalore are pretty predictable, and the variations in quality service are generally not all over the place. I think that's, given the high levels of congestion we have and population, I think that's a good place to start from.
Once you see the other segments also, you'll get more surprises.
Yeah, well, for sure. Okay, anything else? Thank you.
Can you just show what is it for
I'm sorry? Yeah, this is just, again, the IDF perspective from serving content, HTTP2 and Quick are good. Quick, again, solves the problems of latency variations and TCP performance throughput. So that's great. I think this UDP, secure UDP is also something valuable because security by default is important. And with these bike sharing and scooter sharing and these constrained devices coming online more and more, I think datagrams are the way forward. So if your IoT device or your client software can originate packets which are secure, so you can encode the user's location, the user's PII, and things of that nature, I think that's a win. So I would be personally interested in seeing micromobility and personal mobility software stacks using secure UDP in some form or the other.
Great, thanks so much. That was a very, very interesting
Thank you.
and compelling demo. Yeah.